Hi, welcome back for the last time. This is the last week of the semester that we'll be having a video at all. As soon as I'm done posting this video, the final's going up. My suggestion, of course, is to watch this video before you take the final. And then, my other suggestion is, of course, take the final once and then come back and watch whatever videos you need to review and then take the final the second time. You will have 2 shots at it. It will be timed, and the questions are randomized, so they'll come in a different order. So you can't just, use question numbers when you're trying to review for it. Anyhow, what I've done, I've taken a couple of videos that cover the rest of our diagnostic testing. We ended at fuel trim, and there's a lot of other tests that we can do. So I put those together, and anything that's not covered, just so you know, for the final, anything that's not covered, those questions won't be on the final, right? So everything on the final is covered in these videos. So if you've watched all of these, you've seen all the information, right? Not that you're going to remember everything, I get that. But what you can do, right, is if you're not sure about something, after the first time you've taken the final, if you're not happy with your grade, you can go back and review all the different videos. You have to watch the whole thing, but parts of it, and find where that information is, what you're not sure about. Another method, of course, all the videos are based on slides, PowerPoint presentations. So take the test once, go flip through all the PowerPoint presentations. They're all on Blackboard, and see if you can find the answers that you weren't too sure of. Just my suggestion. You do it how you want. So I won't see you again. I won't, be posting another video. For those of you in the seated classes, I am going to be here on Monday, not here, but at the school on Monday, available, if you have questions. And I told you guys, the ones that are in the seated classes, take the test once, right away as soon as I post it, and then come in Monday with your questions before you take it for your final time. As always, if you have questions, if you can't access something, email me right away, because there's not a whole lot of semester left. And once the semester's over, there's just nothing I can do as far as letting you make up stuff, right? So, hopefully you learned something from this video, and good luck on the final. And if I don't see you, have a great holiday, have a great rest of your year, have a great life. And if I do see you, then good.
We just did fuel trim last week. And the thing about fuel trim, that we talked about, let me go back to here, is just as a reminder, it's an indication of how much the computer is having to correct for something that's a little bit off with the engine, or possibly a lot off. So if it's just a small little thing, tiny little vacuum leak, slightly low fuel pressure, something like that, fuel trim can compensate and put the air-fuel ratio right where it's supposed to be, and everything's good. If the problem gets too big, then the fuel trim cannot compensate, and that's when we see a diagnostic trouble code for a too lean condition or a too rich condition. And then the other thing you saw last lab video is when I pulled the mass airflow sensor, the hose off of it, the computer actually knew that was a mass airflow sensor problem. It saw there was nothing, or not even a slightly realistic number coming from that sensor. So it chose to ignore that, and it chose not to use that to into the air fuel calculation. And so our fuel trim numbers didn't even move. They were still very small single digits because the car was using other sensors to calculate the correct fuel delivery. All right, so if we move on to fuel pressure testing, right? So, fuel pressure testing. So there's 2 things that we're going to test here. We're going to test the actual pressure that the fuel pump and fuel pressure regulator combined, what they are supplying to the fuel rail. And the second thing we're going to test is when we shut the key off, when we park the car, is the fuel rail maintaining some pressure for the next startup? So why would we do this test? Well, if we have a no start, maybe we're missing spark, maybe we're missing compression, maybe we're missing fuel. So if we've eliminated spark, probably the second easiest thing is to make sure we have some fuel pressure. On a lot of vehicles, there is a fuel pressure test port right on the rail. You can screw a gauge on. It's no harder than checking your tire pressure. Other vehicles have not included the fuel pressure test port, and so we can't just screw a gauge on. We have to somehow tee into the line. That can be a little more challenging. You need a lot more adapters and things like that because of all the different type of quick connect fittings that are on fuel rails and fuel lines and fuel filters. Sometimes you have to almost make something up. So we'll assume that we have managed to configure a fuel pressure gauge to measure the fuel pressure on your vehicle. So one thing you should know, when you turn the key on with the engine off, there is a 2-second prime that the fuel pump does. So the computer kicks the fuel pump on for 2 seconds, and this causes the pressure in the fuel rail to go up. So the first step here, it says key on, engine off, cycle several times. What we're trying to do is we're running that 2-second prime more than once. The first time we may not get full pressure. So let's take a 50 PSI specification. Let's say 50 is what our fuel pressure is supposed to be, key on, engine off. The first time you turn the key on, it might only go up to 30 or 40. It might take 2 or 3 cycles of the key, but at some point it's going to stop increasing, and that's going to be, your max fuel pressure. That's what you're going to see right there. So, key on, engine off, fuel pressure spec, let's say it's 50. You're going to compare to your specification, see if you have enough fuel pressure without the engine running. Now, most of the time when you start an engine, the fuel pressure will actually go down when the engine's running at idle. So there are various ways that this is done. The early original were a manifold vacuum fed to a fuel pressure regulator. At idle, vacuum is high. That would pull against a spring that would keep the fuel pressure down low. And then as you accelerate and the engine vacuum drops, so if you stomp on the accelerator, you know that engine vacuum can go almost away. It can almost go to atmospheric. That allows, the vacuum goes away from the pressure regulator, allows the spring to push harder and causes the fuel pressure regulator to hold a higher level of fuel pressure. So on idle, you might have, 30 or 35 PSI. Stomp on the accelerator, it might go up to 50. And I'm just pulling these numbers out. So don't go by those. Actually look up the specs for the vehicle you're working on. So you're probably going to have a key on, engine off spec, and you might possibly have engine running at idle spec. And those are the two you want to compare. Keep in mind, if we have a gasoline direct injected engine, then there's really 2 fuel pressures. There's the electric pump in the tank. Some people call it a lift pump. This just supplies fuel to the high pressure pump that's going to be up on the engine, probably driven off the camshaft. So you're not really seeing what pressure is available to the injectors on a gasoline direct inject engine. You're just making sure that your electric pump is working correctly. Most GDI engines, I would say, you can look at fuel pressure, the high pressure side, on a scan tool. You know, it's dangerously high pressure, so you need to be careful if you're working around the high pressure side of the high pressure pump. So right now we're just talking about port fuel injection. We're talking 50, 60 PSI, not super dangerous. Obviously, fuel is very flammable, so if you're working around a hot engine, you need to be cautious not to spill fuel all over a hot exhaust manifold and start your car on fire. So now we've done a regular fuel pressure test, key on, engine off, engine running. We like the readings we've gotten. What do we do next? So if you look at the symptoms on the bottom, no start, hard start, the ones in red, lack of power, surging, excessive fuel trim corrections. Let's talk about what could cause all of these things, all right? So no start, obviously, if our fuel pressure is significantly too low, the engine's not going to start. So, you know, completely plugged fuel filter, bad fuel pump, a hole in the fuel line, something like that. Serious fuel pressure problem. We're going to have a no start. Let's skip over hard start for a minute. Lack of power. If your fuel pressure is low, enough to start the vehicle, but not enough to supply sufficient pressure for conditions where a lot of power is needed, that could be a fuel pressure issue. So it's going to be kind of hard to, you know, I can't really draw very well, but this way, but back when I was in the dealer, station wagons were still a thing. You know, with a big family truckster, and we had a big Mercury 9-passenger station wagon. That was before SUVs came around. And this vehicle, it ran fine until you tried to go fast. As soon as you tried to go fast and it needed all that extra fuel to do it, it just wouldn't do it. At first, I thought maybe we had a plug catalytic converter because we have talked about that. But that wasn't the problem. The problem was there was actually a leak inside the fuel tank. The high pressure line coming out of the pump was cracked between the pump and the outlet of the tank. So a lot of the fuel that was coming out of the pump was just coming out of the pump directly back into the tank and never actually leaving the tank. So the pressure up at the rail was ridiculously low. But the car would do okay idling. It would do okay, you know, driving around town. It was just when you tried to go fast. So that lack of power could definitely be caused by a fuel pressure concern. It should be pretty obvious as soon as you put a gauge on and start it up. Surging. So let's talk about what surging actually is, and that's when the power you're getting out of the engine comes and goes. So you get a surge of power, and then a lack of power, and then power again, and then no power. A lot of times this is referred to as a lean surge, because that typically happens when your air-fuel mixture is excessively lean. Could fuel pressure problems cause your air-fuel mixture to be excessively lean? Of course they could, right, if your fuel pressure is too low. The next one, excessive fuel trim corrections. You know, if your fuel pressure is low, then when the computer calculates injector on time to deliver fuel to the engine, and it opens the injectors for that amount of time, it's not going to be enough fuel because of the low pressure. So what's going to happen, the computer, you know, going back to our fuel trim slides, the computer is going to see we're too lean. It's going to increase the fuel trim numbers so that extra fuel is added, and try to bring it back to the correct air-fuel ratio. So if we have low fuel pressure, we're going to see positive fuel trim numbers as it's adding fuel. If our fuel pressure is too high, we could have the opposite problem, right? We could have where every time the injector's open, they spray too much fuel, so we're too rich. And so we'll see negative fuel trim numbers as the computer tries to take fuel away to get it right. So the hard start one, this is the reason for that last test, the key off leak down test here. What's supposed to happen when you park a car is most or a lot of the pressure that's in the fuel rail is supposed to stay there so that the next time you go to start the car, there's fuel pressure available at the injectors instantaneously. If for some reason the pressure leaves that rail, and we'll talk about what those reasons could be, but if the pressure leaks out of that rail, when you go to restart the car, it won't start until the fuel pump runs, pumps fuel up into that rail, and the pressure gets high enough to start the vehicle. So that could be a long crank time. Instead of starting instantly, it might crank for 3, 4, 5, 10 seconds while we fill up that fuel rail. So that's what we're testing for when we turn the key off and watch the leak down. So what you do is you pressurize the fuel rail to its full pressure by cycling the key several times, key on, engine off. Then you shut the key off and watch. On a good vehicle, the pressure loss should be 5 psi or less when you wait for a full minute, 60 seconds. If your gauge just keeps dropping throughout the 60 seconds, that indicates that there's a problem. And what could the problem be? Well, something's not sealing up. And one of those possibilities, the pump should have a one-way check valve that allows fuel to exit the pump towards the fuel rail, but not leak back. And then the other thing could be, any kind of a leak, any kind of a pressure leak. So fuel pressure regulator, an external leak, a leak in a line, injector O-rings, whatever. Well, not injector. Yeah, top injector O-rings could do it. So if you see this leak down, that could explain a hard start problem. And so you have to try to figure out where that leakage is. The way I've done it in the past is by clamping off return lines, clamp the line off from the pump so that fuel can't run backwards, and see if that fixes it. Yeah, that should about do it for this slide, I think. So we're going to do a fuel pressure test if we have no start, hard start, lack of power surging, excessive fuel trim corrections, and we don't come up with another reason for it. All right, vacuum. This goes back to pretty much the very beginning of the semester, where we talked about atmospheric pressure. We talked about what vacuum is. We talked about what's normal in an engine, what's abnormal. So, quick review, right? Vacuum is just any pressure less than atmospheric. In a typical engine at idle, normal vacuum readings are about 17 to 22 inches of mercury. So how do we see that? Well, you need a vacuum gauge, obviously. And that vacuum gauge needs to be plugged into a source of intake manifold vacuum. So it has to be below the throttle plate. In other words, it can't be outside the intake manifold. It has to be something direct intake manifold vacuum. That used to be really easy to do because a lot of things on the vehicle used to run on intake manifold vacuum. Now, as more and more devices become electrically controlled, it's getting harder and harder to find a vacuum port that you can plug a vacuum gauge onto. Typically still, the canister purge solenoid has a line going directly into the intake manifold. So on some vehicles, that's all you got. And that can be a pretty good sized line, so you're going to have some sort of an adapter for your vacuum gauge. So why would we be doing a vacuum test on a car? Well, again, if you look at the bottom, the red, right? Idle quality. Now maybe we have a rough idle. Idle speed. On some vehicles, particularly vehicles that use a speed density system. That's where it does not use a mass airflow sensor, but it uses manifold vacuum to determine fuel control. Creating a vacuum leak is no different than opening the throttle. It just makes the idle speed go up. On other vehicles, like if you take a carbureted vehicle and you create a vacuum leak, it's going to run very rough, nearly stall. And a fuel-injected vehicle that uses mass airflow, a vacuum leak, depending on how big it is, can just cause fuel trim problems, or if it's big enough, it can cause very poor running. So I have a picture that I'll show you in a minute that can help kind of explain one thing that I ran into once. So we see misfires here. If there's a vacuum leak for one cylinder, that cylinder could misfire, right? Because it's way too lean. How could that happen? Well, one way is intake manifold leak at that cylinder. But another way, I'll show you that picture in a minute, something that I ran into 40 years ago, 35 years ago, that was actually diagnosed as a bad engine, and it was a vacuum leak. Another thing that might make you do a vacuum test, excessive fuel trim corrections, right? Surging, we talked about that with the fuel pressure, or lack of power. So we know that if our vacuum is just low, right? So it's supposed to be 17 to 22 at idle. If it's just low, most likely you have some sort of vacuum leak, right? So you're losing that vacuum somewhere else. Possibly late valve timing could do the same thing, right? It's affecting, if the valves are not opening and closing at the right time, it's affecting how well the engine breathes, which obviously is going to show up on a vacuum gauge. If you look at that second line, severe valve train problems, if you have a stuck valve, let's just think about this, an intake valve that doesn't close, right? Then every time that piston comes up, it's going to push air back out into the intake manifold. What are you going to see on the gauge? You're going to see a needle that bounces severely. I'm not talking just a tiny little bounce, right? But every time that piston comes up, it's going to shove pressure back into the intake manifold. So you'll see a bouncing needle. That can identify valve train problems. On a normal running engine, when you do a snap acceleration, sudden acceleration, as that extra air flows into the intake manifold, the needle on the vacuum gauge will go almost to zero, almost to atmospheric. But then it will quickly catch up. In other words, as the engine speed increases, then the needle will go back into a vacuum, back nearer to that 17 to 22 inches of mercury, right? So it's normal to see a decrease in vacuum as you accelerate. But then as the engine speed catches up, the vacuum catches up too. If the vacuum never recovers, in other words, this is a classic symptom of a plugged exhaust, which could be plugged catalytic converter or anything else. What will happen is the faster you try to make that engine run, the worse it will breathe. The exhaust is blocked. It cannot get rid of the exhaust. It cannot take in new air. So what you'll see for that, you'll see an engine that has good vacuum at idle potentially, but then as you raise the RPM, maybe you go to 2,000 RPM, 2,500 RPM, the vacuum just starts to go away. The needle starts going closer and closer to zero. And as that pressure backs up, a couple things will happen. One, the needle's moving closer to zero. And then secondly, the engine just won't accelerate, right? This is not the same kind of thing you get when you have a rev limiter on some cars. it's killing fuel injectors to keep the RPM down. And so that's very rough. It's the rev limiter. Other vehicles with an electronic throttle control, they just refuse to open the throttle plate in order to get the engine speed too high in park. They just won't do it. The computer is limiting the engine RPM because it's in control of the throttle plate. With a plugged exhaust, the real key is that vacuum gauge, that the engine won't accelerate, and the vacuum gauge is hanging out at a very low number, very close to zero. It just can't get rid of the exhaust, so it can't take in more air. It has no vacuum. One way to verify a plugged exhaust is to physically disconnect it. So if you think your catalytic converter is plugged, disconnecting the exhaust in front of that catalytic converter should make the problem go away. Obviously, it'll be loud, but you'll have good vacuum and good acceleration again. It may be enough to simply remove an oxygen sensor, and that'll allow enough exhaust to escape out that oxygen sensor hole that it makes a big difference. So those are two things you can do to try to verify a plugged exhaust. Some of you, I'm not sure if you all got to see in lab before we got kicked out, I had a back pressure gauge, and we removed an oxygen sensor and screwed this gauge in its place. I know some of you saw it. I don't know, I can't remember if you all did. So that's another key that we can look at. We can verify the vacuum test results with this exhaust back pressure test. And what we saw in that is that exhaust back pressure on a normal engine is very, very low. It was less than a pound, really, under almost all conditions. We got it to go up a few pounds when we literally stuffed rags in the exhaust pipe. So exhaust back pressure is supposed to be pretty low. So here's a picture that I took in the shop of an intake manifold. This is a straight 6. This is on a Jeep. So you can see here the valve cover. You see, I don't know why I cannot, why I can't. Let's see here. Annotate this. Let me try to just share that. See what happens. No, that's not working too well either. Okay, well, it doesn't matter. Hopefully you can see the mouse moving right here, but what you see is this is the intake manifold here, straight 6, right? So here's the valve cover, here's the fuel rail, here's the fuel line coming in, and then each cylinder, right, here's the injector wire for cylinder 1, cylinder 2, cylinder 3 over here, and there's an intake runner for cylinder 1, there's an intake runner for cylinder 2, there's an intake runner for cylinder 3. And notice what's right here is a little vacuum cap. There's a little vacuum nipple that is unused on this vehicle. And so it's just blocked off with a little rubber cap. The experience I had, see if I can, yeah, it's a little better view of it. So the experience I had back years ago, a customer brought a vehicle into the shop, and the customer's concern was they had been to a shop called Auto-Tune. So this was before Auto-Tune had anything to do with your voice or singing or anything. Auto-Tune was a chain of tune-up shops. You'd bring your car in, and for a set fee, they would do plugs, and back then you did distributor cap and rotor and points and whatever was necessary for whatever they called a tune-up, maybe air filter. And then they hooked it up to a big fancy diagnostic machine. So one of the tests the diagnostic machine did was a cylinder power balance. right? So this is something you should be familiar with now, right? Cylinder power balance, and it indicated that one of the cylinders was weak, and so they told the customer, you need an engine, you've got a bad cylinder. So this is not the kind of work they did at AutoTune. AutoTune was just a tune-up shop. So they handed him the fancy computer printout, and in he came. Now, never mind that, rather than bringing the car to us for a tune-up, he tried to save money by bringing it somewhere else. Okay, whatever, we asked him, before we put an engine in your car, do you mind if we just look at it ourselves? And he said, no, go ahead. So almost immediately what we noticed, that there was a setup similar to this. It was a straight six, and there was a vacuum hose. So it wasn't capped off. It was a vacuum hose that went to somewhere, but it was on one of the intake runners. So, think about it. If this vacuum cap cracked or were missing, I guess on this engine, it would probably affect cylinders 1 and 2. It would have no effect really over here on cylinder 3, right? Because the air's coming in, through the throttle body over here and coming in. But as the air flows through to cylinders 1 and 2, and this extra air is being drawn in, those two cylinders are going to be exceptionally lean, and they're going to misfire. So on this one years ago, right, this was not out here. It was more like, say, here in this area right here. So it was only affecting just one cylinder. That cylinder was misfiring. And so this shop had diagnosed it as a weak cylinder when the repair was, you can imagine back in the 1980s, early 1980s, what it cost to repair a broken vacuum hose. It was not a lot of money. Okay, stop sharing this. Okay. So that's just a little story I like to tell. Don't let your diagnostic equipment tell you what to do and override your actual brains, right? So all it took on that vehicle to override this fancy computer's diagnostic that it needed a new engine, all it took was a quick visual inspection. I want to say the entire diagnosis in our shop took a minute and a half, maybe. And after replacing that cheap piece of vacuum hose, the misfire was magically gone and the engine ran fine. So let me stop this, and let's go back to our blackboard here. All right, back to our slides. Here we go. Yeah. So vacuum tests can tell us a lot of things, right? This is why I say, though, it can cause idle quality problems, right? If you're too lean at idle speed problems, too lean could cause it to idle poorly, and idle quality and idle speed kind of go together a lot of times, right? But it could idle too fast because it's getting air in, just as it would through the throttle plate being open, and the computer sees the decrease in vacuum, so it adds fuel. That's not on a mass airflow. That's just on a speed density car. Misfires, we just talked about that. Excessive fuel trim corrections, okay, if we're too lean because of a vacuum leak, we're going to get fuel trim corrections. Surging, same thing, lean surge. And then lack of power, we talked about possibly plugged exhaust. So a vacuum test can help us diagnose that. Okay, let's move on. Here's something that we've been through in the shop. So this shouldn't be new to you, but just to make sure that everybody's on the same page and everybody understands exactly what we're doing here, right? So a compression test, and let me skip to the bottom of the next slide, right? Why would we do one? And, misfires, hard start, no start, or lack of power. So depending on what symptom we're trying to diagnose, we're looking for something different out of a compression test. If we have misfires, we are probably looking for one cylinder that is different than the rest. If we have hard start, no start, or lack of power, we may be looking for some sort of a problem that is connected to all of the cylinders. So think about what kind of problem that could be. So how do we do the compression test? Well, obviously we need a compression tester. We want the engine ideally to be warm, but not hot. Why? So why do we want it warm instead of cold? Well, when engines are manufactured, all of the tolerances, clearances, things like that are all specified for an engine at operating temperature. So when an engine is at operating temperature, all of the clearances are where they're supposed to be. When the engine's cold, those clearances may be different. So the engine is designed to run most effectively, most efficiently at operating temperature, because that's where it's going to spend most of its time. The reason we don't want it hot is there's a little bit of a problem with removing spark plugs. Didn't used to be that big of a problem when cylinder heads were cast iron, but now that most cylinder heads are aluminum and spark plug shells are still steel, these two materials have different expansion rates. And because of the different rates of expansion on a really hot engine, the spark plugs can get sort of locked in to the spark plug ports, spark plug holes, to the point where if you force them out when that engine's really hot, you may take aluminum with you. You might take the threads right out of the cylinder head. That's not something you want to do, because that can turn a diagnostic test into a major repair. You may need to remove the cylinder head in order to fix that. That's not something you want to get into. Now, can you always do a compression test on a warm engine? Well, no, because if you look again at the symptoms, one of the symptoms could be no start, right? And on a no start, how do you warm up the engine? You don't, right? So you're doing it on a stone cold engine, probably 60 or 70 degrees, whatever temperature that wherever the vehicle's been sitting. We want the throttle wide open. Now, this used to be a really easy thing to do, but unfortunately, it's not necessarily a really easy thing to do anymore. When throttles were operated by cables or linkage, we could just open the throttle with our hands while this test was going on, or just step on the accelerator pedal while the test is going on. Now with electronic throttle bodies, on a lot of vehicles, you have to use a scan tool and put the vehicle in compression test mode. And what compression test mode does for you, it will open the throttle, it will disable the ignition and the fuel injectors. So it's actually kind of convenient, but you have to know about it. In a minute, we'll go on all data and we'll look up for a particular vehicle the compression test procedure, and I think you'll see that it's one that you use a scan tool for. Now, in an older vehicle, you don't have that option. I used to tell my students that opening the throttle as opposed to closed throttle didn't make that much difference on a compression test. But I always pay attention to, and I always make the students do it both ways. See what happens if you don't open the throttle. See what happens if you do open the throttle. And I think it might have been a Honda this semester where there was a really significant difference in the compression pressure we got when we didn't open the throttle. When we didn't open the throttle, the numbers were way lower than they were with the throttle wide open. So, that's kind of convinced me that regardless of the vehicle, I want to have the throttle wide open during a compression test. We remove all of the spark plugs. I'm not going to say that I've never done just a single cylinder. If I knew that a particular cylinder was misfiring and I just wanted a quick check to see if the problem was compression related, I've done it. Just pop a plug out, screw the gauge in, crank it over, see if I'm at zero on that cylinder or close to it. But for the most part, if we're doing a full-on compression test, removing all of the spark plugs will make it real easy for the starter to crank the engine over. It will put the cranking speed where it belongs for the compression test, where with the min, it'll be cranking slower than it should. And it's much easier on the battery, much easier on the starter, on the battery, everything, So pull all the plugs, connect a battery charger. You're going to be operating the starter quite a bit during this test, so that is going to have a tendency to bring the battery level down. Install the compression tester and then crank the engine. So one cylinder at a time, we're going to put the tester in, crank the engine. The important thing here, right, is to be consistent. Do every cylinder the same way. I'd like to say that I can give you an exact number of how many engine rotations or how many compression strokes you should do on each cylinder, but I have seen some that say 5 compression strokes. I've seen some, and I'm talking about factory directions, right? Some that say at least 5 compression strokes. And I have seen some that say until the gauge stops going up, so getting maximum compression. And I guess, this really is a function of how they came up with the specification they're giving you. What we want to do is we want to do each cylinder twice and then average the 2 readings you get. Compare those readings to specifications and compare those, every cylinder to the other cylinders. And the lowest cylinder should have at least 75% of what the highest cylinder has. How do we interpret the results? Well, if one cylinder is low, then that cylinder has a problem. Got a valve that's not sealing, rings that are bad, damage to the piston, blown head gasket, I don't know. If 2 cylinders that are next to each other are low, they are probably leaking into each other. So where the cylinders come close together, blown past the head gasket from one cylinder into the next. If all the cylinders are low, or all the cylinders on a bank with overhead cams are low, it probably indicates a problem with valve timing. Now, we had a really obvious one in the shop this semester, that Subaru, with all the valves bent. There was no compression in any cylinder. So that is a systemic problem, if you will. It's not, not just to one cylinder. But what caused the valves all to be bent? It started out with a valve timing problem, right? A broken timing valve. See if I can pause things a minute here. Okay, it took me a minute to get this up on the screen for you. Make sure that I'm where I want to be here. Come on. All right, we are. Okay, so I have brought up a what a pain. Brought up on all data this 2015 GMC Sierra that we were talking about, or that I used in the lab, right? And under powertrain management, I just actually searched, I think, let's see, I'm just going to search compression test. Too many S's. Engine compression test. So, okay. It's under powertrain management, tune-up and engine performance checks. So, we need a spark plug port adapter, right, for the compression tester. But here's the part that I was telling you about. All right. They want you to run the engine until it reaches normal operating temperature. You might want to connect a battery charger during the test. Remove the spark plugs and connect the scan tool and select compression test. So what it does then is it disables the fuel pump, fuel injectors, and spark. The throttle body is open to wide open throttle position. Also, the scan tool will automatically control the cranking procedure on some vehicles. If cranking control is not available, use a remote start switch in place of the starter relay to control cranking. So that's where you hook a switch right to the starter motor. And then they have you crank the engine, and it says 4 compression strokes. So like I was telling you, some vehicles say 4, say 5, some say crank it to get the maximum reading, you know. And then they give you a very low ball 100 PSI as a minimum. And here they're giving you even a wider range here. The lowest can be as low as 70% of the highest reading. I don't really like that, and I'll tell you why. 70%, if I had a car and the lowest reading was 71% of the highest, I really wouldn't expect that vehicle to run that smoothly. But that's their standard. That's what they give you. Remember, you're doing this test because you're trying to diagnose something. So you're already looking for either a misfire, a hard start, no start, lack of power. If I have a misfire and I find one cylinder is only, the lowest cylinder is only 70% of the highest, and that's the cylinder that's giving me a misfire, I'm going to call it a compression problem, definitely, So in general, and we look at all these tests that are available, in general, let me just say, you're going to do these tests from easiest to most difficult. On a lot of vehicles, compression test is going to be near the last thing that you do, right? Because it's typically pretty easy to check for spark. A lot of times it's pretty easy to check fuel. So you may never get to the compression test when you've already identified the cause of the misfire. But if you're here, then you've probably eliminated spark and you may have eliminated fuel already. So you're looking for something, and you know what you're looking for. If it's a hard start or a no start, you're looking for low compression kind of across the board. Same with lack of power. If you're looking for a misfire, then you're thinking that compression is, low on one cylinder possibly, and that's what you're looking for. So let me stop sharing this. Let's give me a minute here. And don't mind me. Start the video a little bit here. Okay. So I think that's about all the talking I can do for this week. Hopefully you stuck with me and listened to the whole thing. We're getting near the end of the semester, so obviously, the next test you take is going to be the final, and it's going to incorporate everything that was on the last test, plus the stuff we're talking about right now. And a lot of the stuff we're talking about right now is not necessarily new to you. We talked about compression tests back in the first couple weeks of the semester. We didn't talk about it so much in the lecture, though. We talked about it out in the shop. So there will be questions on it. Questions, like what does it mean if two cylinders next to each other are low? What does it mean if all the cylinders are low? Technician A says that the engine should be, warmed up. Technician B says you have to let the engine cool for 8 hours for a compression test. Who's correct? Things like that. Just to make sure that you understand what it is we're trying to do. Cylinder leakage. How do we do it? Well, first thing we do is we look at the bottom here in red, or, the question is, why would we do a cylinder leakage test? The answer is compression test failure. And I know I discussed this in the shop, but let's just talk about it again for a minute. A cylinder leakage test can be time consuming. It requires you to put the engine in specific positions for each cylinder. So if you have an engine that things are difficult to get to, you don't want to do a cylinder leakage test just for kicks. The best reason to do a cylinder leakage test is this. You've done a compression test and one or more cylinders have failed. If you've done a compression test and all the cylinders tested good, that would be like trying to find the leak on a tire that has good air pressure. If a tire has a leak, how are you going to know? The pressure is going to be low. If a cylinder has a leak, how are you going to know? The pressure is going to be low. So if it passes a compression test, you'd be looking for a leak that's not there. If it fails the compression test, now the question is, okay, we're losing pressure, where's it going? And there are really three major possibilities there. It's escaping through the intake valve back into the intake manifold, or it's escaping through the exhaust valve into the exhaust manifold. Excuse me. Or third possibility is it's escaping past the piston down into the crankcase. And if it's escaping past the piston, there's a couple possibilities there. You could have scored cylinder walls, so even brand new rings wouldn't be able to seal. You could have compression rings that have lost their tension from overheating or something like that, or they're stuck from carbon, or they're just worn. You could have, I've seen pistons with holes in them. So the pressure is going right through the top of the piston down into the crankcase. So what we're going to attempt to do with a cylinder leakage test is find out which direction the pressure is going. Is it going out the intake? Is it going out the exhaust? Or is it going into the crankcase? So let's take a look at that cylinder leakage tester for a minute. You're familiar with the cylinder leakage tester. We used it in the shop already. So this is just really review, nothing new. If I take the cover off this here, slide it out, and we'll get that back in frame. So two gauges on the leakage tester. There's the gauge that's the input pressure that comes in from the shop, and then the gauge that's actually in the cylinder. And so shop air is attached here. This comes out, shop air is attached there, and the other end goes to the cylinder. Put that back in. And then we have adapters that fit the cylinder. So notice these do not have a Schrader valve in them. And we talked about that, how the compression testers have that one-way check valve in them, but the cylinder leakage tester does not, because air has to be able to flow backwards through this hose into the cylinder, not just out. So the basic procedure here is to attach shop air to the fitting, and then we have an adjuster knob that allows us to set the air pressure on the input side. And the easiest way to do this is to set it to 100 psi, because we're looking at percentages when it comes to leakage. And so if we have this to 100 and the cylinder holds 90, it's going to show as a 10% leak. If it holds 80, it's going to show as a 20% leak. There are times, and we talked about this too, when you have a small engine where 100 psi applied on top of the piston causes the piston to be pushed down in the cylinder, which takes it out of the position it needs to be in for the cylinder leakage test. And if you remember, for cylinder leakage, we have to have the piston at top dead center on the compression stroke where both valves are closed, so the cylinder will be sealed up. If the piston gets pushed down in the cylinder, then it's no longer in that position. Air leaks out through one of the valves that's now open, and the test is useless. I've always been told that up to 10% leakage is absolutely normal. This gauge, the green, yellow, and red on this gauge are a little bit different. It has almost up to 40% in the green saying it's low. And then from 40 to about 70% says moderate, and anything over that is listed as high over here. So this is, you know, right here, this is 20, this is 40, 60. I'm telling you, if you have a cylinder with, you know, 35% leakage, that's not normal. So if I did a cylinder leakage test, even though that was in the green, if I'm much over 10, I'm going to start thinking I have some sort of a problem with that cylinder. So the way this gauge is labeled, I don't necessarily really care for, but the basic procedure, and we did it before, right, is you blow air into the cylinder at a set pressure. You see how much pressure the cylinder holds. There's always a little bit of leakage. Anything up to 10% is absolutely normal. A brand new engine would do that. Now when you get above 10, it indicates you have some leakage, and if it's, you know, 20, 30, 40%, you've got a fair amount of leakage, and that could start affecting your compression, definitely. So back to the bit about the small engine. Sometimes 100 psi is too much, and so the piston gets pushed down. If that happens and there's no way to lock the crankshaft, what you may have to do is set your input gauge to 50 psi, and that means everything's cut in half on the other side. So zero leakage would then be 50 on the output side, right? And if you had 45, that would be 10% leakage. So we're at increments of 10. So this would be 0, that's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100% leakage. So if I was at 50 for my input PSI, that would be here. You know, here, if both needles were pointing straight up, I have 0% leakage. If this was 5 pounds off, you know, then I would say that's 10% leakage, 5 out of 50. So you wouldn't be able to go by these percentage numbers on the scale over here unless you're using 100 psi on the input side.
So we used the tester. We've completed the test. We've blown air into each cylinder one at a time. And let's just talk a little bit more about that. How do you know when a cylinder is at top dead center on the compression stroke? Well, for cylinder number 1, there may be timing marks that you can look at on the front of the engine that allow you to know when cylinder number 1 is at top dead center. That will not tell you whether it's on the compression stroke or not. So another way you can possibly tell if a cylinder is on top dead center is to insert something physically into the cylinder, and you have to be careful with this. We demonstrated this. We put a long 1/4 inch extension through the spark plug hole and slowly turned the engine by hand, and we could see the
extension rising as the piston, approached the top of the cylinder. And then you could tell when it stopped moving and started moving back downward, we had just gone over top dead center. So that's a way to tell that we're at top dead center. Now, how can you tell you're on a compression stroke? You could just try it. In other words, you're at top dead center, so blow air into the cylinder and see if it holds. And if it's 100% leakage, you're on the exhaust stroke, if it's all coming out the exhaust valve. But another way to do it is screw in the adapter and cover the end of the adapter with your thumb and start bumping the engine with the starter. And as the piston's coming up on a compression stroke, you're going to feel pressure building against your thumb. So you'll know it's on the way up on the compression stroke. Then you can remove that adapter and you can put your dial indicator or a screwdriver or that long extension like I showed you and finish turning the engine by hand to find top dead center. So the pressure building against your thumb tells you you're on the compression stroke. And then the physical, observation of something in the spark plug hole can tell you when you actually hit top dead center. Once you establish top dead center on cylinder number 1, you could just use math or use the degrees, right? So a 4-cylinder engine has a compression stroke every 180 degrees. So if your firing order is 1342, you've just completed your cylinder balance or cylinder leakage test on cylinder 1, the next cylinder is 3, and it's going to have a compression stroke exactly 180 degrees after cylinder 1. So 4-cylinder engine, it's every half a turn, every 180 degrees. So you could just turn the crank 180 and cylinder 3 would be ready to go. Another 180, cylinder 4, another 180, cylinder 2, and you're done. If it's a 6-cylinder, it's every 120 degrees. And an 8-cylinder is every 90 degrees. So that's one way to do it. You have to be really exact, though, turning the engine, counting, how many degrees. Half turn's pretty easy to figure out. Quarter turn, pretty easy to figure out. That 120 degrees can be tough. So you can get close that way, then maybe you want to verify top dead center with the method of using a screwdriver or a dial indicator or something to make sure you're right at the top. Okay, so I've done all the cylinders. How do we interpret the results? If we're here because of a compression test, really the cylinder we're going to be concentrating on is the cylinder that was low, the one that failed the compression test. If they're all low, that could be like we talked about with the compression test, that could be some sort of a valve timing issue or something like that. But one cylinder low, maybe it has a burned valve. Maybe it has a bent push rod that's not allowing the valve to close. Maybe valves are bent. We saw an engine in the shop this semester with all the exhaust valves bent, right? Maybe there's a problem with the piston or the rings. So how do you determine which it is? And that's really simple. You just listen for where the air is escaping. So if I have a stuck exhaust valve or a burned exhaust valve, when I do a cylinder leakage test, I'm going to hear air escaping at the tailpipe. If I have a burned or bent or stuck intake valve, I'm going to hear air escaping at the throttle body. When I put it in the cylinder, it's going to come out the throttle body. And if it's a lower end problem, rings or something with the piston, that air is going to get by into the crankcase, so I'm going to hear it at the oil fill cap. So it's really a simple mechanical thing, this cylinder leakage test. You're basically doing the same thing you do with a tire. You're blowing air in and seeing where it comes out. It's not really complicated. So let me just go back to the slides here a minute to make sure I didn't miss anything. So rotate engine to close both valves for the cylinder being tested. Check. Apply air with the tester set at 100 psi. Check. And we had that little discussion a minute ago that we might have on a small little engine. If we're using 100 psi, then it's really easy math. Every pound is a percent. If we're using 50, every pound is 2%. So if we blow 50 in, and we've got 5, that's 10%, and I'm still 10% leakage. And like every other spec, if it was 11, would I say that's definitely the problem with the engine? Well, maybe not. That snap-on gauge allowed us 40, but I've done this test on a lot of good engines, just demoing it, and it's always less than 10 on engines that are running well. So take that for what it's worth. Here's an example of a test that was, I guess, more useful in the past. Not so much now, but timing advance. Years ago, and so if you're working on an older car, this might still apply. Especially, this was on distributor cars mostly. The timing advance, or the which is electronic, could be disabled usually by unhooking some sort of a wire. So when you were going to hook a timing light up and check base timing on an engine, you had to disable the timing advance. So this test was designed to see if that timing advance system works. And so it's a really simple one. Following the manufacturer's procedures for disabling the timing advance, which is usually disconnecting an advance wire. You're watching with a timing light or with a scan tool, or even with your ears. When you disconnect that advance wire and it drops back to base timing, that'll be seen on a timing light. It'll be heard in an engine RPM drop, and it could be seen on a scan tool. And then when you reconnect that wire, the RPM recovers, the timing advances, and you may be able to see that on a scan tool. So this is a test that was more useful when the computer was telling the ignition module to advance the timing. It was verifying the communication between the two. Now the computer is completely in charge of when the spark plug fires, so this test has become kind of obsolete. I keep it in here because it's a reminder that retarded ignition timing, or timing that's not advancing properly, can cause two symptoms, and they are lack of power and poor fuel economy. So if you have an engine that's exhibiting both of those symptoms, but otherwise running smoothly, we're not misfiring, stumbling, anything like that, there may be a problem with ignition timing. And depending on the vehicle, diagnosing that would be radically different. So most modern vehicles is completely controlled by the PCM, and there isn't really any way to test it. Next test, and this is why I kept all these for the end, is because they've been obsoleted by newer technology also, but you may not be working on newer technology, so this is a good thing to have in your toolbox. And I did this a demo in a lab, but cylinder balance test. If you suspect a weak cylinder, right? So you have a misfire, or it feels like a misfire. So you know that one cylinder is weak. You're trying to figure out which one. What do we do now? Now we look at the scan tool, we read the code. If cylinder 3 is misfiring, we got a P0303, cylinder 3 misfire, we know which one it is. There's nothing else to do. But if you're working on a car that's a little older, pre-96, doesn't have misfire detection, the only way of identifying the cylinder that's causing the problem is doing some sort of cylinder balance testing. So what we're doing here, right, is we're disabling one injector at a time and looking for an RPM drop. Now, one of the problems with doing that is, since the computer is now in charge of engine RPM, engine idle speed, when you disable that injector and the RPM drops, it's quite likely the computer is going to turn around and correct that RPM and bring it back to where it's supposed to be, even though you're missing one cylinder. So you may see this effect when you kill that injector. You may see an RPM drop for a short period of time, and then it recovers. So you got to watch right away. You just have to be aware that the computer can correct that low RPM. Some of the earlier cars, you could disable the computer-controlled, the idle air control valve. But now I'm going to say with electronic throttle bodies, there's really no way to disable that. So the computer is completely in control of the throttle body motion, and it has a target RPM it's looking for. And so anything that throws the engine off that target RPM, the computer is going to correct for and put it back where it wants it. So there'll be, besides a drop in RPM, you should notice definitely a noticeable roughness. And on a 4-cylinder engine, it's going to be more noticeable than it will be on an 8-cylinder, because you're killing 25% of the engine. So here's what you do, right? If you don't have misfire detection, disable one injector at a time. So since we have to stay generic here, I got to tell you, the easiest way to do that is to pull the electrical connector off the injector. Look for a drop in engine RPM. Cylinders that don't cause an RPM drop are not contributing. So if you pull an injector and it has no effect on the engine, it tells you that that cylinder wasn't doing anything in the first place. Killing it made no difference. It doesn't mean the problem is with the injector, but it means there's something wrong with that cylinder. No spark, no fuel, bad compression, and then the other tests, compression, cylinder balance, all that, those are designed to find out which of those it is, right? So this is just trying to identify a weak cylinder, which one is weak. What if you have direct injection? You're not going to be able to do this, right? You're not going to be able to pull the wires. You may not be able to even get to any kind of connector. You can coil unplug. You can disconnect the low voltage connector from that coil. It'll stop the coil firing. Same effect, that cylinder will stop operating, and there should be a noticeable RPM drop, at least temporarily, and there should be a noticeable decrease in idle quality. So this is, like I say, okay for older vehicles. It's okay for things that are not even cars. You might be working on something that's not a car. But on a modern vehicle, what are you looking for? You're looking for a misfire code. So I throw these things out here because I don't know what you're going to run into in the future. I know if you're working at a dealer, you'll probably never run into a vehicle you need to do this on. All you'll be doing, for the last, 24 years, right, is looking at a misfire code. Okay, one more test in your toolbox. This is kind of no-code diagnosis stuff, right? If you don't have a code telling you exactly where to go, is the injector balance test. To really give you an idea of how this works, I have to demo it in the shop. But here's the essential, steps involved. Somehow pressurize the fuel rail. How do we pressurize the fuel rail? We talked about this with the fuel pressure testing. We cycle the key. So every time you turn the ignition on, you're going to get a 2-second prime. And the fuel rail, at some point, is going to reach its maximum, regulated pressure, say 50 or 60 psi, and then no matter how many times you cycle the key after that, it's not going to make a difference. So you got the fuel rail pressurized. You manually activate the injector. So we have a special tool that will connect directly to a fuel injector. right to the electrical connector. And with the push of a button, it'll fire that injector for, I believe it's 100 milliseconds. When that injector fires, you'll be able to see a pressure drop in the fuel rail as fuel flows out of the rail through that injector into the intake manifold. So the idea is you do this on every fuel injector and you compare the pressure drop on each injector with all the other injectors. Some things to be cautious of, right, is every time you fire that injector, you're putting liquid fuel directly into the intake manifold. You almost need to start the engine between every cylinder just to clear out all that fuel, or you'll be flooded. Or even worse, if you do one cylinder multiple times, you can actually hydrolock the engine. We had it happen. An instructor was doing a demo with the Ford scan tool, and the Ford scan tool just runs through, it automates it. It's kind of nice. It runs through and it fires each injector, and then it repressurizes the fuel rail, and then it fires the next injector, then it repressurizes and it fires the next injector, and it just runs through like an 8-cylinder engine in less than a minute. They're all done automatically. It controls the injector firing. And so the instructor was demonstrating this, but then did the demo and then had a student do it, and then had another student do it, and then had another student do it. And so every time this test runs, fuel is spraying out of the fuel injector into the engine. And what happened is, after several students did this test without running the engine, when they tried to start the vehicle, there was so much liquid fuel in the cylinders that it actually bent connecting rods. You can compress a gas, but you cannot compress a liquid. So that's known as a hydrolock. So it's not good. Anyhow, the idea here, right, is you start from the same pressure every time. So between cylinders, you need to repressurize the fuel rail. And the more accurate of a gauge you have, the more you're able to tell if all the cylinders are flowing the same amount. Why would you do this test? Well, if you had misfires, rough idle, which could indicate a leaky injector, hard start, excessive fuel trim correction. Right, so these are kind of potential fueling problems. So like I told you, some of the tests that we just talked about, you may not find much reason to do in this day and age because of the advanced diagnostics built into the PCM on the car. It can tell you, if there's a misfire, it'll tell you what cylinder it is. So you may never need to use some of these, but you might be working on older vehicles. I don't know, you might be working on a tractor, a boat, an airplane, and these things can come in handy. So now we've kind of reached that stage where we've talked about all the various diagnostics, maybe not everything that's possible, but most of the various diagnostics out there. And so now the question is, once we have identified the cause of a customer concern or the cause of a malfunction, now what do we do? Kind of an obvious answer, right? We fix it, but we don't just stop there. So let me talk about that a little bit. So I had it was an old Plymouth. They don't even make Plymouth anymore, but the vehicle had no heat. And I determined that the engine was not reaching operating temperature, and that's why there was no heat. You could see it on the temperature gauge on the dash. It just barely moved off of cold.
The heater hoses didn't feel hot. So, if your heater hoses aren't even getting hot, the heater core is going to be cold. I don't care what you do with a blend door or anything, you're not going to get heat. So I was young, foolish. I went up to Kmart and I bought a thermostat, and I put the thermostat in and refilled the cooling system, bled it, and I'll be damned, still no heat. So I began to doubt my diagnosis and think, well, maybe there's something else. But then again, engine's not reaching operating temperature. There really isn't another explanation except for a bad thermostat, one that's stuck open. So back up to Kmart and got another thermostat, put that in, filled the system, bled it out. Same thing, no heat. Now I'm walking away from the job saying, I don't know what to do. It has to be the thermostat. The engine's not getting hot. It's not like somebody installed an extra good cooling system, right? Everything else is the same on the car. It's all factory stuff, and the engine's not reaching operating temperature. There's only one possibility. It's the thermostat, right? So this time I went to a actual parts store, and I bought an actual better quality, better brand, spent a little bit more money, and put that in, and car had heat all day. Absolutely perfect, fixed it. The problem was never the diagnosis. The diagnosis was correct right from the start. But the problem was that I was using crap parts, for lack of a better term. And so here's the thing, we all might be motivated to try to save money or to try to save our customers money. But if you're redoing a job 2 or 3 times, you're not saving anything. So you have to really be cautious about where you get your parts, the brand names you put in. I mean, I use Rock Auto and places like that all the time, get them online, but I buy part brands that I recognize, that it's the same thing you would get at a parts store. It's a brand that's been around forever, and not just something that I've never heard of that happens to show up online somewhere. And sometimes the price is more, but I have confidence that when I'm done with the job's going to be done, right? So use quality parts. And then the other part, industry standard repair practices. I had some heater cores, that's just an example, a heater core, can be extremely difficult to replace. It means removing the entire instrument panel, the entire dashboard from the car, removing the heater box, getting it out on the bench, separating it, replacing the heater core, putting it all back together. And so I heard of a guy, just saying, well, I'm not going through all of that, and just hacked a hole in that heater box, changed the heater core, and then slapped the heater box back together with some JB Weld or super glue or something. And my thought was this: that's not your car. You don't have the right to hack it apart like that. When somebody brings a car to you, they have a right to expect that the repairs you do are going to be up to published procedures that the manufacturer has recommended and approved. Does that mean the shop manual is always absolutely correct on every step you need to take? No, I don't think it does. I've seen some pretty stupid things in shop manuals where they have you doing absolutely unnecessary steps. But the thing about the shop manual is it's almost like a legal document, right? If you follow what's in the shop manual, and an attorney were ever to ask you, why did you do what you did? If you can point to the shop manual and say, because the shop manual said so, then you have nothing to worry about. That's your defense, right? That same attorney says to you, why did you do what you did? And
brings up the shop manual and says, why didn't you do this? And you said, well, I didn't feel like doing that, or I thought my way was better. That's kind of indefensible, right? You had clear instructions of industry approved procedures and you went off on your own. And so you're taking that responsibility now on yourself. So just be aware of that. I know you're not always going to do things absolutely by the book, every single step. You know it, I know it. I've been around long enough to see it. But people that are good at this, they stay pretty close to the shop manual. And they don't have comebacks. They don't have failures. They know the sorts of things not to do, the shortcuts not to take. And that can take years of experience. So it's always at least safe to follow the shop manual procedure. That's why we try to teach it here, before you do a job, bring up all data, bring up the procedure, follow that. Is it absolutely the fastest way? Not necessarily. Is it the best way? Maybe not. Is it an acceptable way that is going to keep you out of trouble? Well, it should be, right? So leave the hack jobs for the beer swilling backyard guys. And you want to do this in a professional manner, the repair, and work within industry standard repair procedures. So now you've done the repair, now what? Do we ship it, hand it back to the customer, hope everything went okay? Probably not the best way of handling things. So always within whatever you're capable of doing, however you can do this, something else you want to do is verify the repair. So let's take a look here. So we've done the repair. We want to verify and retest. So let me stop my video here. There we go. So we want to verify and retest. If we had codes, diagnostic trouble codes, we want to verify that they've been cleared. In most cases, a road test is called for. Verify the symptoms are gone, and to verify the code doesn't come right back. Now, obviously, some of these things, like, well, I'll give you an example, an evap code, small leak, large leak, that can be kind of difficult to verify or repair on a road test. Reason being, getting that evap monitor to run probably involves an overnight cold soak and then some driving. So it may not be practical for something like that to absolutely verify the repair before returning the vehicle back to the customer. So in that case, that should be explained to the customer that the monitor won't run until the vehicle sits, and I'm sure they don't want to leave the car for a week so you can go through and make sure all the monitors have run. But for other things like misfires or lack of performance or stalling or idle quality problems, etc., if you were able to verify that the condition existed before you did your diagnosis and repair, you should be able to verify that the condition does not exist after you've done your repair. But here's one caveat, one thing you have to keep in mind. Some symptoms only show up when the engine's cold. Some symptoms only show up under load. Some symptoms only show up when the engine's hot. Maybe on a cold day, maybe when it's raining out, I don't know. But in next semester's class, we're going to talk about the term similar conditions and what it officially means for OBD2, the terminology. But essentially, it's the same temperature and load conditions that existed when you first verified the concern. So if the problem's at idle, you're going to verify the repair at idle. If you verified the symptom at wide open throttle, you're going to verify the repair at wide open throttle. If it only happens on a cold engine, obviously you want to make sure that it no longer happens on a cold engine. So the road test has to be under similar conditions. And then recheck to make sure they didn't return. You can't just go on the malfunction indicator light, because some or a lot of codes nowadays take 2 failures before they'll actually illuminate the malfunction indicator light, the check engine light. And they won't set a code, a current code. What they'll set is a pending diagnostic trouble code, meaning that the monitor has failed once, but it's a 2-trip monitor. It has to fail twice to set a code and turn on the light. So if you do the road test and then verify that you don't have any even pending codes, then you know the problem didn't recur, at least during that road test. Very important.